at producing an improved global biomass map, mostly for modeling purposes. Regarding biomass mapping, actually, in fact, I will mostly focus on the tropics, and then at the end of the presentation, I will go to the global scale. For the tropics, you may know that in the last years, there's been two main biomass maps that have been published for the pantropical region. The datasets from Vaccini and the datasets published by Sacchi et al. And which have been used also for various applications, such as also estimating emissions from deforestation. However, the two datasets are quite remarkable, but they present some disagreement, and recent papers from Mitchard et al. Look a bit more in detail in the differences between these datasets. And an example, we can see that actually the total stock tends to converge at national scale or at regional scale, but the spatial patterns of biomass is quite different. This is just an example for the Congo Basin, where these are the difference between the two maps. And in the blue, you see the areas where the Sacchi datasets estimates biomass more than 100 tons compared to the Vaccini datasets, and the opposite is in the red areas. So in terms of spatial distribution and the local estimates, they are quite different. And this is a bit problematic from a user point of view, because once you have only one map, it's fairly easy. You probably just use these datasets or not. But once you start to have two maps, you have to decide what to do. To choose one, or maybe you want to take the other one, or maybe make an average, if this makes sense. So that's a bit why we're trying to think, okay, well, how can we deal with these differences? So basically, this study and this talk is about acquiring new independent reference data on biomass, and used to assess where we have data, how the maps perform, and then use this information, hopefully, to combine these maps in an optimal way. So we'll briefly present the methodology and then the application for Africa. So the first main task was to put together all this biomass data, this reference data. And we collected mostly field plots, so from forest inventory or research networks, and also high-resolution biomass maps. So maps produced in, let's say, local scale with high-resolution data and a large amount of field data. And we defined some quality criteria in order to acquire all the data that can be considered can be used as a reference for this study. So we try to get the same variable and define some constraints regarding the timing and the spatial resolution of this data. And here you can see the current data set for the tropics about field plots and maps. But this is still, I mean, it's ongoing. We are still trying to, it's a leading data set in the sense where there is more data available, I mean, acquired that they were trying to access in order to fill more the gaps. After acquiring the data, it's necessary to process it. Since we want to use this data to compare with the pantropical maps, which are 1 kilometer or half kilometer resolution. So for the case of the field plots, we need to upscale the value that is measured on the field to 1 kilometer, which is quite not an easy task, since usually the area measured on the ground is between a quarter hectare to 1 hectare, and we want to upscale to 1 kilometer. So the first, this is so to do that, we just simply look at high-resolution data on Google Earth and see, is this plot representative of the area on the ground of the pixel of the two maps according to the tree cover. And we just discarded the cases where obviously this is not, because there is a heterogeneity in the pixel. Similarly, for the where we have some biomass maps, we also aggregate the maps of 1 kilometer, and then we only take the pixel which have been produced using where there is reference data, where field data on the ground that have been used to calibrate the map. This is an example for Uganda, where a national map, we only took basically the pixel within which there are field plots, which represents at least 40% of the pixel area. So this is just a strategy to try to take the data that we think are more reliable, since this should be used as a reference. And then, anyway, by aggregating 1 kilometer, then of course the amount of points that we have tends to decrease. This is just a summary of the data sets for Africa. And you see on the left the distribution of reference data, which goes quite to a large range of biomass. And the area of the measure on the ground for 1 kilometer pixel. You see, most of the times is between half and 1 hectare, but there are also some large plots. And then so we end up, for the moment, we have about 667 points for Africa. But as I said, the idea is to improve this. So once we have compiled these data sets, we can use it to look and compare with the pantropical maps. And this is just so this is the comparison by pixel for the maps. And you see on the x-axis we have the reference data, on the y the biomass maps, and see on the left the Sachi and the Center Pacini, and on the right the average of the two maps. And they present somehow some sort of similar trend. It's interesting to see that in this case, averaging the map does not really improve it, but not also make it worse. But we can look a bit more for specific context to see how the maps perform. And I here pull out two cases. The one on the left, I just took the data acquired in the Congo Basin for undisturbed forest. These are mostly data collected by the Rainfall Network. And you see that in this old-grown forest with high biomass density, the biomass maps tend to underestimate the biomass. Instead, on the right you see the opposite case, and this is only looking at the dry vegetation areas in Eastern Africa. Where compared to the reference data sets, the pantropical maps both tend to overestimate the biomass. So once we know we have this knowledge of the error, we can use this knowledge to try to improve the maps where we can. And we are doing it using a sort of fusion approach, so combining these maps using the reference data. And by first assess the bias of the map by region and removing the bias, and then make a weighted combination of the maps, defining the weights on the base of the error structure of the input maps of the pantropical maps. And this exercise is done by strata. So because for each stratum we can assess an average bias and one set of weights. So it is also important to identify strata that capture the error of the map. So strata which the error is homogeneous, because even if it's large, but it is homogeneous, it's possible to correct it more efficiently. So minimize the error variance in another way. And we look at different way to stratify using land cover maps or tree cover, tree height. And the most one additional way is to combine this data in order to estimate the error of the map and then stratify by the error. However, we also have to contain the number of strata, because we need to have reference data for each strata. So of course, the larger the strata, the less accurate will be the correction. And so this is somehow constrained by the reference data. So when we apply this method for Africa, that's a bit how the preliminary results, where you see the Sachi and Pacini maps originally, and then the fuse map, the outcome of it. Also in this case, it's interesting to see that the total biomass it's fairly similar to the value estimated by Sachi. However, the spatial distribution is somehow different. And here we see a bit what we saw before, that there is a bit of higher estimates in the old-grown forest and lower estimate in the fused map in the dry vegetation. And this is also we estimate the error, and this but this is the error only estimated by the reference data, so it's not really an independent validation. So not surprising, the fused map tend to have a lower RMSC. We can also look how this, what's the outcome for these two specific case studies, the Congo Basin on the left and the dry vegetation on the right. And in both cases, so the fused maps can estimate higher biomass values at 1 kilometer. And there is still, of course, some scattering in the estimates, but there is no substantial bias. So that's a bit one of the interesting aspects of this method. And I put global biomass in the presentation. In fact, I only work on the tropics, so I was a bit cheating by putting global biomass in the title to attract your attention. But in fact, it's because within this the geocarbon project, we want to produce a global map. And what we do is that to combine these tropical maps with the maps produced for the boreal and temperate region that was presented this Tuesday, 2 days ago by Martin Turner, and was developed using the volume map produced by Maurizio Santoro. And so that's what will come in next month is a combination of these two data sets for a global data sets on forest above ground biomass at 1 kilometer resolution. So I'd like to then basically to conclude this presentation, always also looking at what we can do next. I mean, what we can do to improve this study, and there is a lot to do, of course, to improve the estimates of biomass. So these are just a few points related to this specific approach. The first one is not really, it's just somehow a comment that it's very important. There is existing data, but it's really important to be careful with the data in their use, because the accuracy of the I'm talking now about the reference data, so the field data mostly. It's important to harmonize the definition, make sure that we are looking at the same variable, and because what is measured on the field can have different definitions and different accuracy. I also think it's important to acquire new data, especially in areas which are underrepresented, so acquire or actually access data that is existing. But if you also want to go to coarse mapping, coarse resolution mapping, it's also important to acquire data on the ground that can be easily upscaled to coarse resolution, or to use intermediate high resolution maps for this upscaling process. And the last point is about the quality of this reference data, and I think it's also important to remember that the field data are not true to the true biomass. They are not measurements of biomass. This is measurements of 3 parameters which are converted to biomass using anometric equation. And in the tropics, usually we use generalized anometric equation, which are quite large uncertainty, which will then propagate throughout the whole chain to the map. So it is important to improve the allometry. Or another way to do it, partially of course, is to use a new technology, which is the terrestrial LiDAR. And I will just present one case study of this about this technology. This is one of the topic of the PhD of Kim Kalders, which is one of our PhD students, and he was a poster on this study. And he compared the estimate biomass using this terrestrial LiDAR, and for a case study in Australia for an eucalyptus open forest where about 150 trees were destructively harvested, and the biomass was assessed. And this is the preliminary results only for 6 trees, but they're very encouraging because this tool is able to very accurately assess the volume of the tree, and then from this, using good density, we can have an estimate of biomass which is comparable to by the destructive harvesting of trees. So this would help to avoid the use of allometric equation and also avoid to cut the trees to measure the biomass. But of course, this is a new technology, and now there is more testing done in the tropics, and we are working in close collaboration with the University College London, and there will be a presentation in the afternoon about the application of this technology also in the tropical region. So with this, I would like to thank you for the attention, and also thanks all the many co-authors of this study, which also share the data, and without which this study would not be possible. So, thanks.
Thank you very much. So one question, Dennis.
Thanks, nice talk. You answered my one question about the accuracy of the reference data, but the other question I have is, when you compare the data from Sacchi and Bacchini, I noticed the Sacchi data is saturated. So I guess my question is there a physical reason that the Sacchi data saturates, and therefore could that be also a limitation and a bias? And then when you come up with the fused data, is that actually the right answer? And that's an important figure. What's your comment?
Yes. The saturation, where I think there are two things to consider. The first one is that if we go back to the you see here in the fuse map, does not saturate. However, this is first one can be an artifact of the fuse map in the sense of actual reference data, in the sense that this is biomass measured for one plot. And then we assume that we have 51 kilometers. We assume that the biomass in 1 kilometer is the same that in 1 hectare. And of course, usually when you have a larger area, biomass range tends to decrease. So maybe the real biomass in 1 kilometer will be a bit lower than what we saw in the upper left graph. However, it seems there is quite a strong, let's say, saturation of the Sacchi and Bacchini maps. I think this depends on the reference data that they use for calibrating their maps. There are a number of reasons that can be related to density, but they use mostly field data to tree height, and then use this to estimate the biomass. And I haven't really looked too much into that, but I want to. But I think it's probably they didn't have so much reference data in this high biomass forest, and so that's the relation height to biomass was not capturing this very old this forest with high biomass.
So are they both using the same radar and the same radar bands then? Is that also part of the question?
They use a similar, the same kind of remote sensing data, which is LiDAR glass data and MODIS data mostly, but different modeling approach and different field data. So there was a study that I mentioned at the beginning, which looks really to understand why the estimates are different or what is driving the estimates. It's not that clear, but it's there are a number of reasons. But probably in this case, I would think that their reference data, the training data actually the users explains most of the difference.
Why is that you think that the reference data is the one that drives this relationship? Why you don't think in a simple thing like NDVI and this kind of approaches saturate with increasing biomass?
Yes, that's for sure, because since they use MODIS data to make the map, there is a saturation. But they also use hundreds of thousands of glass shots. So this is a remote sensing estimate of tree height. So if you have, there is quite an information on this in the map. So if the tree height increases, the biomass increases. Also, it should relate also, even if the MODIS signal, of course, there is some saturation. But still, I think it's the underestimation is so large that I think that if they have more plots in this in this high biomass forest, also the modest data would show it, because it's just like a matter of calibration.
Thank you. Yeah, more questions there?
Hi, I just wanted
Yeah,
to.
I know. Only flexibility, life needs to be flexible in 5 minutes.
Thanks. I just wanted to respond to Dennis's comment that the biomass information comes from the LiDAR height, and the way that they process the LiDAR height is slightly different. And a lot of the differences seem to have arisen. There was another paper that did a third way of processing it that came up with a different answer again. And so it kind of depends on how you aggregate the spot information from the LiDAR height and then convert that to aerial height and then convert that to biomass. And they don't have so many footprints over the high biomass, which is, just what you're saying, that if you only have a few and you underestimate height by a couple of meters, you miss a large chunk of biomass.
So thank you very much to the speakers, and I don't know what Fred is going to tell you,